Welcome to the last submodule of the first module of Yellow Belt Training, which is Six Sigma Fundamentals. This submodule, Module I3, covers quality tools and metrics. I'm a certified Six Sigma Black Belt with the American Society of Quality, and I'll be conducting your training. Or Ishikawa fishbone diagrams, check sheets, control charts, histograms, Pareto charts, scatter diagrams, and stratification, which is the concept of dividing data up into categories or taking slices of it. Oftentimes you'll see flow charts or run charts listed as the seventh basic quality tool. Both of those stratify data up into, in the case of flow charts, you stratify your process up into steps, and in run charts, you're stratifying by time series. So it's the concept of dividing and slicing data up to get useful information on what's vital to your process. The check sheet is your basic data collection platform. You collect information on the frequency of occurrence, usually a defect or undesirable event. So when you create a check sheet, you specify the data and the factors for collection, determine the time period, construct the form. You want to pilot or test the form to make sure that it works good in data collection. This is basic data collection form and basic data collection methodology. Here we see a basic check sheet where by day of the week they're collecting information on a defect by event. So in the column there we see the different kinds of unacceptable occurrences: structural damage, cracked weld, no test record, etc. And you could literally make a mark whenever the process person finds that case of a defect. And then in the other view there, they're simply summed to their numerical totals. So we can see that immediately scratches is the number one occurrence by count of frequency of the types of defects being monitored. This is the beginning of a Pareto chart, which is one of the other basic quality tools that we'll be going over shortly. And the bar chart, once ranked, and with a little bit of additional information on the cumulative percentage, turns into a Pareto chart. Depending how you visually arrange your check sheet, you can actually get a sense for the distribution. Here on the left, we see a check sheet by date and the completed repairs. Well, we could put that in terms of frequency counts, and we can see that 4 is the average or mean value of repairs. So you can actually get some visual information out of a check sheet depending on how you arrange it physically. The LSL and the USL is lower spec limit, upper spec limit. So that's something we'll be talking about a little bit more also, which we can see visually here with this check sheet with proper arrangement, those number of repairs that are falling outside of our desired limits for number of repairs. We can put this in a dot plot of frequencies, and we start to see the distribution, and we can put it in a histogram, which is the count of frequency using bars, and we're going to cover that here shortly. And we can plot the same information, and we can put a lower spec limit and upper spec limit. So off the check sheet begins your basic frequency data or counts of defects that you can begin to use in your basic tools for analysis of your problem. There are different types of check sheets. This one is called a traveler check sheet. It travels around with the product, hence its name. In each process step, the operator enters the appropriate data. It's a good way to collect data on lead time. Depending on the type of problem you have, this could be a very powerful tool to understand the nature of your problems. You take a map or a figure and you can mark where the defects or problems occur. This location check sheet is often used, as we see from TV, on murder investigations, and I believe that a location check sheet was what helped them discover the cause of typhoid, where they could mark illnesses and locations of waste disposal. A location check sheet can also be on top of a cause and effect diagram. This is a variation of a cause and effect diagram, which we're going over shortly, and you can see where you have a particular problem is occurring. You can mark it in the area of your causes to your problem. 80-20 rule, or the law of the vital few, that states that for many events, roughly 80% of the effects come from 20% of the causes. 80% of your profit may come from 20% of your customers. 80% of your absenteeism may come from 20% of your employees, and so on. Named after an Italian economist, Vilfredo Pareto. It helps you define project scope. It helps prioritize potential vital factors and root causes. It's simply, in its simplest form, it's a bar chart count of an item, often errors or defects, arranged from largest to smallest, with an additional plot of cumulative percentage of all the factors, as we'll see here in a moment. Pareto analysis is used all through the phases of DMAG. It's very often used in define, frequently used in measure and analysis to stratify data, look what your potential root causes are, even help you analyze what the factors are that are causing your problems. Improve, you can weigh improvement options by Paretoing the benefit, cost versus benefit. It's a very frequently used basic quality tool in process improvement. Of errors by category. So we have the different sections that report the number of errors. So you sort the errors from largest number to smallest. That gives you your basic bar chart ranking. And then as you see there, you do a cumulative total of the number of errors until you sum to 100%. That's plotted on the right x-axis there under percent, and then you have the number of errors. So you see the basic traditional Pareto chart with number of defects in the bars ranked from most to smallest and the percent, cumulative percent. Now the traditional breakpoint to consider factors to be the 20% of the factors that are causing 80% of the effect is 80%. That's the Pareto principle. So we see there at section L with the errors of around 18 or so, it's starting to accumulate to about 80% of all the errors. And that's called the vital few, or those are the factors that you want to focus on. And then you have the trivial, or sometimes called useful many. If you're talking about people, you talk about the useful many. If you're talking about inanimate objects, you have the trivial many. So you have section G, section J, and to some extent section L are your critical report sections for focusing your improvement. Now we can use the basic quality concept of stratification to take section G, which is our biggest vital factor, and we can do a Pareto of that. So we see that reporting errors out of section G, bank address, and illegible entry and placement are the top categories in section G with respect to number of errors. Now, if you don't see the Pareto effect in a set of data, and you have what might be called a flat tato, where you don't see anything standing out, it's quite possible you haven't got things stratified in a way that really identifies a category of interest. Now, in this case, if we combine computer password and computer access into computer issues, we see that we start to see computer issues as a category that is a vital factor. If we were to realize that telephone was also basically a information systems issue, then we see that IS issues is a clear vital category for problems with, say, new employees in this case, or contractor problems, I should say. Cause and effect diagrams can be thought of as a graphical representation of the 5 whys. The 5 whys is an iterative question-asking technique used to explore cause and effect relationships for a root cause. The primary goal of cause and effect analysis and using the tool fishbone diagrams or 5 whys or in conjunction, the primary goal of these techniques is to determine the potential root causes of a defect or problem. Once you identify the potential cause, it must be verified as a root cause with data. Five whys are fairly straightforward. You select any cause and effect and ask why it occurs until you believe you've reached a root cause. This is a fairly famous example of the 5 whys. The Washington Monument was disintegrating, was the problem. It was the use of harsh chemicals, and you could keep asking why until you got down to the point where you found that really the root cause was gnats. They're attracted to the light at dusk. So if you turn on the lights at a later time, it will help mitigate the problem. And I believe this is a factual case of one thing they did do to help the monument. Now, there's nothing magic about 5. The objective is to drill down until you believe you have an actionable item, something you can get data on so that you can verify it as a root cause and have a solution that will achieve your improvement results. Many times, cause and effect diagrams are a visual representation of this principle, and cause and effect diagrams and 5 whys help push the team beyond symptoms to uncover root causes. You want something you can get action on, you can get data on. You want it to, of course, it'll need to be within your manageable boundaries, something that you can get data on and do something about. It's a form of a brainstorming tool. It's often used early in the measure phase to generate ideas for finding potential critical X factors. And it can be used in improve and control phase for proactively for prevention of problems, to brainstorm weaknesses in the future state, for implementing planning of the future state. A little less often used purpose for the cause and effect diagram, but certainly can be used for that. This is a pretty much full cause and effect diagram. You see you have the problem statement in the head of the fish, and you have major categories of environment, measurement, methods, people, materials, and machines. There's no standard set for the major headings. These are typical. Once you have a major heading, you can drill down, say under environment, there you have equipments and temperatures and that level down. And then what's wrong with the environment? You have a problem with the equipment, and then what's the problem with the equipment? And you drill down until you find some issue with the equipment under the environment that you can go out and you can collect data for and see if it is something you want to attack as a vital factor in your improvement process. And there's a summary of the developing the fishbone diagram as we just saw. For production processes, you can have those 6 M's. For service projects, you can have those 5 P's. You can really have any major categories that make sense. Usually you will have things like manpower, machines, environment, material. There's typical general categories that affect all processes. The specific name you give to them would be up to the team. And then you use a diagram to brainstorm for more detail into the factors that are causing your problem. Again, you try to get down several layers, hopefully at least 3. If you think you're on a bone of the fishbone diagram that is high potential and that the team feels is a good path for a cause, you should go down at least 3 levels. Another example of a fishbone diagram. Now, similar in purpose to the fishbone is to identify potential critical X factors with several Y factors. Helps quantify potential X factors. It's a basic decision matrix we saw before. It's similar to a Pugh matrix or a voice of the customer matrix. Helps organize and prioritize brainstorming results. And then you can collect data on what is the most important X's to you. Can be updated and used in later phases, such as implementation and control for selection, for weighing and selection options there. So the process for creating a cause and effects matrix is you review the process map, and you list the output variables of interest, and you rate or weigh each of them, usually 1 to 5, 1 to 10. You identify potential inputs or independent factors that can impact the various dependent Y factors, and then you rate each of them on the matrix, and you can calculate a rank and a percent rank, and you can use that to prioritize team activity. Usually you use a Pareto chart of the results. We notice that the dependent Y outputs are in the columns, and we can tell that because they're the ones that have weighting to them. So customer importance up there is ranked 1 to 10, where we forced a ranking, which is often done, of giving ranks of 1, 3, or 9, which is always a good idea to force a spread ranking. It helps you get differentiation between your factors. But we see there in the Y's are in the columns with a weighting. Now sometimes you'll see matrices where as we saw in an earlier example, the dependent variables were in the rows, but the weighting followed them. So usually in a cause and effect matrix, they are in the column headings, and there's the weightings, and along the rows are your various various process inputs associated with the process step. So this is a very typical cause and effects matrix. And there we have the different rankings. We see, for example, under the process step of serving the coffee, the putting on a holder was the first input there that had an effect on temperature of coffee, and it was a high effect. And cover the coffee has a high effect on temperature of coffee. We go up under clean the pot process step. The cleaner is rated as having a 3 or a medium effect on the taste of the coffee, and so forth. A blank cell indicates no perceived relationship. So we can score by multiplying the cell ranking value by the weighting and getting a total. And we can then Pareto the results so that we see then that selecting the coffee and putting on the holder are a couple of the most, at least the team decided by the use of this tool, selecting the coffee, putting on the holder, covering it, and measurement of the coffee, rinsing are some of your top. After you get to about rinse there, it starts to flatten out. So measure coffee, cover, put on the holder, and select the coffee are determined to be some of the vital factors in customer satisfaction with the cup of coffee.
We'll now go over the basic quality tool, histograms. Histograms are frequency plots. A graph is used to assess the shape and spread of the sample data. To draw a histogram, you divide the sample values into many intervals called bins. Bars represent the number of observations falling within each bin. In the histogram below, for example, there are 3 observations between 0.5 and 1.5, 6 between 1.5 and 2.5, and so on. To construct a histogram, you take the difference between the max and min values from the sample, divide this range into even intervals. Now, too many intervals exaggerate the variation, and too few hide the variation. Usually you make histograms with statistical analysis tools, and they usually do a good job of dividing up the intervals for you. You count the number of observations in each bin, and the bar height represents the count in each bin or interval. Now you can fit a continuous distribution to the attribute count of sample values, and you can use this continuous distribution line to predict probabilities. Now, these distribution lines can be generally overlaid with actual data values, so you can directly compare the empirical value to the hypothesized distribution. So here we see a normal curve fit to the histogram. Here are some of the questions a histogram can help answer. First of all, it helps us determine normality. Now, there are many statistical tests out there that will test data for normality. It's hard to beat visually looking at your data to making judgments about normality. It gives you an idea whether the data, if it's not normal, is skewed to the left or right. If there's tight clustering, it can help you tell you if you're just staying within desired set limits or specification limits. It can tell you if you have actually helps you tell if you have 2 distributions when you think you have 1. You see here bimodal, or two basic patterns, indicating you probably have 2 separate distributions at work when you might have thought you had 1. Here are some other questions a histogram can answer. I'm not going to go through all of these, but you can go and you can find lists of help you, guide you to look at many kinds of distributions and what they might mean, but usually the user of a histogram can look at it and, in the context of the problems he's trying to solve, be able to tell quite a bit of information about what the distribution is telling him with respect to his understanding of the process. Now, summary statistics from samples. There's 2 basic qualities we want to look at in a sample. We want to look at its central tendency and distribution. The central tendency, or the location statistics, give us the mean and the median and the mode, where the median is the middle value where half the numbers are above and half the numbers are below. The mode is most frequently appearing number. With respect to the distribution of a data set, we have the range, which is the difference between the smallest and largest numbers, the variance, and probably the most used indicator of distribution, standard deviation. The sample mean is the arithmetic average. Again, the median is the point halfway above the data and halfway below the data, and the mode is the most frequently occurring data point in the distribution. Here we see the normal curve, or the Gaussian normal distribution, and it's the baseline for continuous probability distributions. It's a baseline for how we analyze processes and compute probabilities of items falling within or without certain ranges. This case shown is a special case of a standard normal curve, which means it has a mean of 0 and a standard deviation of 1. Here we have a non-normal distribution. Right skewed means that the median is to the right of the mode and the mean is to the right of the median. Left skewed is the reverse. Standard deviation, we'll be covering distributions again under measurement phase. And here's the formula, standard formulation for standard deviation of a sample. The standard deviation is the most common measure of dispersion on how spread the data is. The greater the standard deviation, the greater the spread in the data. The variance is the square of the standard deviation. Now we'll go over under basic quality tools, control charts, which is really time series plots and run charts and control charts are basically the same type of chart with varying levels and different kinds of information. Time series plots plot data in sequential order. The points shown are in order of occurrence relative to the distribution mean or median. It helps show if a process is changing over time. Run charts or time series plots can help in analyzing process changes. A run is defined as a series of consecutive points that do not cross the median or mean and can be compared to expected values. Now, control charts are run charts that have the added feature of control limits that show the expected range of variation in the process. Control limits are generally plus or minus 3 standard deviation from the mean, and these are actually usually calculated for control charts using sample size specific anti-biasing constants. So in other words, statisticians have worked out formulae for calculating plus or minus 3 standard deviations from the mean that take into account sample sizes, and they're called anti-biasing constants. And they're really the ones in statistical software, or if you calculate by hand, you'd go to tables and they calculate the control limits. So if you were to hand calculate standard deviation using a standard formula, it wouldn't quite match what you get on control charts because they use these adjusted constants for the spread of the data based on sample size. The control limits and trends and runs of a control chart help identify common random process variation from any special cause variation that is not normal and random and natural to the process, but rather something that has likely some assignable cause. Now, a scatter plot is another basic quality tool. It's the tool that begins us down the path of regression analysis or understanding linear relationships between variables. A scatter plot shows the relationship between two factors or variables. You must have two measurements for each data point, an x and a y. A line or quadratic can be fitted to the scatter plot. A line is linear regression. A positive slope represents a positive correlation. A negative slope is a negative correlation. The more it has zero slope, the more there's no correlation. A SYB is good to identify x and y's. By convention, y is the dependent variable and x the independent variable. Now we're going to go over basic Six Sigma metrics. We're going to look at calculating sigma for discrete data and continuous data, understand defects, opportunities per unit, defects per unit, defects per opportunity, and defects per million opportunity. We can look at the relationship between sigma, DPMO, and yield, and how to calculate sigma from discrete data. And we can also understand how to calculate sigma from continuous data. Now, we haven't covered continuous and attribute data yet. This will be covered in measure. But continuous data is variable data, measurements of infinite divisions such as time, distance, location. Attribute data is count data such as pass, fail, yes, no, short, medium, tall, or nominal, which is color, red, blue, green, etc. Here are some key definitions for Six Sigma metrics, which are process performance metrics, or critical to quality metrics, are all terms that apply the metrics for Six Sigma. We have defect, which is anything that does not conform to a customer standard. Unit is the product, information, or service used by a customer. An opportunity for a defect is a measured characteristic on a unit that needs to conform to a customer standard. A defective is when an entire unit is deemed unacceptable because of the nonconformance of any one opportunity for a defect. So a defective may have multiple defects. Defects per unit is the average number of defects observed when sampling a population. So it's the total number of defects divided by the total population. Defects per opportunity are the total number of defects divided by the product of the total number of units times the opportunity for defects per unit. Defects per million opportunity is DPO per million opportunities. So you multiply DPO by a million, and DPO and DPMO are various ways to represent your measurement that are used in standard ways in industry. Yield is the percent of good product measured in percent. Yield and defects are complementary, so your percent of defects, 1 minus your percent of defects, gives you your yield or good product. First pass yield, also called throughput yield or rolled throughput yield, represents a product that has made it through a multi-process defect check, has made it through a process without rework in any of the steps. So you have 3 steps in a row, none of them had a defect. Your yield at the end is a first pass yield or rolled throughput yield. For continuous data, again, yield equal 1 minus the probability of a defect or your percent of defects. And it's your percent probability of a defect is based on the standard normal distribution. For discrete data, you get a Poisson estimate of 0 defects using defects per unit. Yield will equal e to the negative DPU. And estimating DPU for calculating process sigma, for defects below 10%, we find that values converge to e to the negative DPO. So your calculations for attribute, process capability, and continuous tend to be the same for low defects, whether you calculate them on an attribute basis using a Poisson distribution, which is a discrete probability method, or you use a continuous probability method such as the standard normal curve, which has that probability density function or the area under it. When for low yield values, you tend to get the same results. For high yield values, you get the same results for low defect, which is low defect rate. Process sigma is the performance of a process determined from the distance of the process mean to the nearest specification limit in units of standard deviation. Z-value, Z-score, benchmark Z are terms for process sigma. Now here let's look at calculating process sigma. Take 2 distributions, both have a mean of 100, and we're going to put on both of them an upper specification limit of 103. The standard deviation for the upper data is 1. The standard deviation for the lower data is 1.5. Now the sigma level for the upper is 3. There are 3 standard deviations between the mean and the upper spec limit. or one standard deviation is 101, two would be 102, and three 103, so three fit in there. The lower graph has a wider distribution with the same mean. Its standard deviation is 1.5. Only two standard deviations fit between the mean and the upper spec limit. Therefore, its sigma level is 2. Sigma level is the distance of the mean to a specification limit in terms of standard deviations. It is also known as the z-value, the benchmark z, and the z-score. The standard deviation is calculated from the data. The larger the standard deviation, the more spread in the data, and the fewer units of standard deviations that can fit between the mean and given specification limit, and the smaller the sigma level would be. This is why variation contributes to defects, and minimizing variations will minimize your defects because you'll be further away from the line where you make defects. Now, the Greek symbol sigma is used for both sigma level and for standard deviation. Context must be used to differentiate in your mind whether you're talking about the sigma level, which is a capability to meet product without defect, or you're talking about sigma as in standard deviation, and of course they're related. So this is certainly a source of confusion that you'll want to try to keep straight in your mind. When you're calculating sigma, the fundamental method is you'd ask yourself, is the data discrete or continuous? If it's discrete, you calculate the defect rate, or defects per million opportunity, and you look up sigma value in a sigma table. For continuous, you identify the distribution, set the specification limits, and calculate yield, and you can convert yield into a sigma value using a standard normal distribution or a sigma table. Now here we have an example of calculating process sigma. Process produces 40,000 pencils. There's 3 types of defects that can occur, and for a total amount of potential defects per item of 6. So we had blurred printing, 36, wrong dimensions, 118, rolled ends, 111, for a total of 165 defects found. So the defects per unit are the number of defects found over the number of units, which is 0.004125. This gives a yield of e to the negative DPU, or 99.59%. Parts per million defects is DPU times a million, of 4,125. Now we can also calculate a sigma value based on defects per opportunity. So we had 165 defects over 40,000 units times 6 opportunities per unit, or 0.006875. We convert this to million defects per million opportunity by multiplying by a million, giving us 687.5. So the yield is 1 minus the DPL times 100, which is 99.93125% yield, or good product. Now from a standard sigma table, this sigma level is 4.7, which can be considered what we call short-term sigma level. Now here we see a standard Six Sigma conversion table that can be found in any handbook. We see where we got the sigma of 4.7, and that's what they call a short-term sigma. Short-term sigma is long-term sigma plus 1.5. The data is shifted 1.5 from the value we'd find in a standard normal table. Sigma tables usually always put the 1.5 shift in, and it represents what the process is capable of in a long-term perspective. This is called the process entitlement. It represents what the process could achieve if common variation over time could be eliminated. Now, yield and defect counts can be calculated before or after defects have been detected and corrected or dispositioned. The formulas are the same, but they infer different results. First pass yield is also called the roll throughput yield. the true process capability, since it represents product done right the first time and does not include the hidden factory. Fixing things not done right the first time represent a hidden factory that adds no value to the customer. So we see here in this process that first pass yield are those defects rate found in the first pass. The final pass yield would include those that were repaired and eventually scrapped. Now, roll throughput yield represents the probability of successive steps or defect opportunities to be defect-free. Here, for example, we have 4 units, each containing 4 opportunities for a defect. There are 3 defects and 2 defective units, assuming any one defect can cause a reject. The probability of no defects causing a reject can be estimated by a discrete probability function called the Poisson distribution for x equals 0. So here we see the defects per unit equal number of defects over number of units, 0.75. The roll throughput yield then can be estimated on a probability basis to be 0.472. We can expect an average of 47% defect-free units that have not been reworked based on this sampling that we have taken here. Now, roll throughput yield represents the probability of successive steps or defect opportunities to be defect-free. If we know the individual probabilities for a defect opportunity on a unit, we can calculate roll throughput yield as a product of the probabilities of the yields. So in this case, now we know the probabilities of each defect that could cause a reject. So it's the product of all the probabilities of the potential defects. So in this case, we can expect an average of 31.4% defect-free units that have not been worked using this method. Similarly, the roll throughput yield being a representation of a defect-free process the first time through. If we know a process, probability for a defect in each process step is shown here. We can use the multiplication of all the probabilities again to get the roll throughput yield for this process of 5 steps. And again, we can expect an average of 31.4% defect-free units that have not been reworked. Now we're going to talk a little bit about lean-specific metrics. Lead time, cycle time, and throughput are often mixed up together and need to be taken in context. Cycle time is the average time for a particular step to complete on an item. The unit is time per unit. Throughput is the number of items produced in a given period of time, where the units are units over time. Throughput is determined by the cycle time of the process of constraint, which is the slowest process step. Throughput is often called and confused with lead time. Lead time and cycle time are related by work in process in the entire process. The units of lead time is elapsed time. It holds to a relationship described by Little's law, where lead time times work in process equals cycle time of the constraint times work in process total, or lead time equals work in process divided by throughput, where throughput is determined by the constraint. Takt time, the rate at which the process must output completed items to satisfy customer demand. Takt is the German word for drumbeat. Units are time per units. Takt time is equal to the reciprocal of the throughput that will satisfy customer demand. So let's take 40 widgets produced in 500 minutes. Takt time equals 500 minutes over 40 widgets, or 12.5 minutes per widget to satisfy the customer demand. Minimum throughput then would be the inverse of that, or a 1 widget every 12.5 minutes. If throughput is not achieved, demand will not be satisfied. The number of people, if it can be calculated, if the generation of a leg requires 30 minutes in a table process, it can be considered a step. With cycle time 30 minutes, and assuming it is a one-person step, several people could perform the step. If the takt time is 16, then the number of people equals cycle time divided by takt time, or 1.87 people to do the job, or 2 people to do the job would be required to keep the takt time. Setup time, also known as changeover time, is the time to convert a process step, such as a machine, from producing one product to producing a different one. Generally speaking, when it comes to Lean Six Sigma metrics, all processes can be measured in terms of quality, that is, defects or effectiveness, and time, which is efficiency or velocity. And process costs flow from these 2 basic types of metrics. Reducing costs without focusing on reducing defects and time will be suboptimal in short term, with long-term negative consequences. One will be your primary metric, where you focus on improving this metric, while you hold the other as a secondary metric and focus on not improving the primary metric at the cost of the secondary metric. For example, your primary metric might be defects and your secondary cycle time, or vice versa. Which you choose to be a primary or secondary is situational and may even reverse in the course of a project, and it may drive the types of tools you use. Your cost of poor quality is a function of your effectiveness and your efficiency. Lean Six Sigma practitioners believe that you can increase quality and reduce time and improve safety with your improvements when they're optimal. They need not conflict. We're going to talk a little bit about the cost of poor quality and reducing the cost of poor quality. Basic cost of poor quality is non-value added activity and defects, where value added means that it does useful work on a product or service, it changes the form, fit, or function, and the customer is willing to pay for it, and it's done right the first time. All else is non-value added. Variation leading to defects, which causes product being outside specification limits, is a core cost of poor quality. Cost of poor quality is results in poor margins, unsatisfied customers, increased claims, added costs, poor morale, and safety risks. Costs of poor quality are those that would disappear if every task were performed correctly every time. COPQ is the difference between the theoretical minimum cost and the actual cost. Improving products, processes, and service is a continual cultural thing, with 3.4 parts per million defects being an acceptable, achievable goal, and that's the Six Sigma level. Actual cost minus minimum cost equal COPQ, or cost of poor quality. Now, the cost of poor quality is sometimes hard to identify in total in its totality. Poorly forming processes fail to efficiently achieve the critical to quality objectives cost money. Appraisal costs, prevention costs, internal failure costs, external failure costs, and hidden costs are all embedded in cost of poor quality. COPQ is a summation of all these costs, where hidden costs yield an iceberg, where most of the costs are made up of unseen costs. Cost of poor quality translates to dollar benefits, and Lean Six Sigma practitioners like to always put the benefit as best they can from a project in terms of dollars. This is best done in coordination with accounting and finance, who are experienced in calculating dollar benefit. Hard savings are those that directly affect the income statement with cost or revenue, and soft savings are those that will affect the income indirectly over time, such as time savings or risk reduction or improved market position. Documentation of COPQ helps the organization measure, prioritize, and sustain improvement programs, and helps effective product pricing. The goal is to reduce cost of poor quality, non-value added costs, towards true or value added costs, and not to cut into fair profit or have an uncompetitive price.